You're downloading a huge game update, right? Or maybe streaming a high-res movie. The internet feels fine, other sites load, but this download just stalls. Or your VPN, virtual private network, suddenly stops working for certain sites, but others load perfectly. What's going on here? It's not your bandwidth, it's not the server. It's a silent killer lurking beneath the surface of the internet. This isn't random. It's a structural limit, a digital speed bump that your data just smashed into. We're going to simulate this failure. Watch closely. I'm going to ping a remote server. Normal, small packets, right? Look, they fly through. 0 packet loss, perfect connectivity. Now, let's try something different. What if we send a massive packet, like really big? See that? We asked the network to send a packet so big, it just vanished. What just happened? It says packet too big, but too big for what? This isn't a conspiracy. It's MTU, Maximum Transmission Unit. Every network interface, every router, every link in the chain that makes up the internet has a maximum packet size it can handle without breaking it up. Think of it like a tunnel. Your car fits, a truck fits, but an oversized load? Nope, it gets stopped. The ping command failed because we deliberately tried to send a packet larger than the local MTU of our network interface, and we explicitly told it, do not fragment. So, our local network usually has an MTU of 1500 bytes. That's for Ethernet. But why 1500? And what happens if the packet could be broken up? Historically, if a packet was too big, routers along the way would just chop it up, fragment it. The problem? Fragmentation caused huge headaches, security vulnerabilities, performance penalties, and debugging nightmares. That's why, by default, your operating system sets a special flag on outgoing packets, the Don't Fragment bit. It's silently telling the internet, if this packet is too big, just drop it. Don't try to fragment it. This Don't Fragment bit forces the internet to use something called PMTUD, Path MTU Discovery. It's how your computer finds out the smallest MTU along the entire path to its destination without ever breaking a packet itself. When your computer sends a large packet with DF-set and it hits a router with a smaller MTU, that router doesn't just drop it silently. It's supposed to send back a special ICMP, Internet Control Message Protocol message, type 3, code 4. Translation: packet too big, fragmentation needed but DF-set. Your computer then reduces the size of its subsequent packets to fit that new, smaller MTU. It's a negotiation. But what if that ICMP message never makes it back? This is where the MTU black hole happens. Imagine a strict firewall along the path that says, ICMP, no way, blocking all ICMP. Your computer sends a large packet with DF-set. It hits a router with a smaller MTU, which drops it and dutifully sends the packet too big ICMP message back. But the firewall blocks it. Your computer never gets the memo. It keeps trying to send large packets. They keep getting dropped, and your connection just dies. It's a silent killer because your computer never knows why it's dying. So how do you find this phantom MTU black hole? We use TracePath, or MTR, my traceroute. Look at this. Running TracePath to a remote server, it shows each hop along the path and its discovered MTU value. You can see it adapting, negotiating. But if you see a tracepath that just hangs or shows no reply after a certain hop, especially when testing with large packets, you've probably found your black hole. That's the firewall or router silently dropping packets and the MTU feedback. This MTU chaos is a huge problem for VPNs. Think about it. When you connect to a VPN, your original packet gets wrapped inside another packet. That's encryption. That's tunneling. That extra layer adds overhead. If your local MTU is 1500 and your VPN adds 60 bytes of header, Suddenly, your effective MTU inside the tunnel is only 1440. If your computer doesn't know this, or PMTUD fails, your VPN connection will constantly try to send 1500 byte packets that are now too big for the tunnel. This is why VPNs often mysteriously break for specific websites or large file transfers. This isn't just about connectivity. Fragmentation and MTU are historically and still can be attack vectors. Remember how I said the "don't fragment" bit was crucial? Back in the day, attackers could craft intentionally overlapping or malformed fragmented packets. Some operating systems would crash trying to reassemble them. Classic denial of service. Even today, if a firewall isn't properly configured or is stateless, an attacker could try to split a malicious payload across multiple tiny fragments, hoping the firewall only inspects the first fragment, missing the real intent. It's like hiding a dangerous message by tearing it into tiny pieces and mailing them separately. So, how do we fix these MTU nightmares? For users, if your VPN or large file transfers are breaking, try temporarily reducing your network interface's MTU. For network administrators, ensure your firewalls are stateful and that they permit ICMP Type 3 Code 4 messages. These are not attacks, they are essential network feedback. Block ICMP echo requests, ping, if you must, but don't block the Path MTU Discovery messages. If you're building applications, never assume a default 1500 MTU. The internet is a variable beast. Understanding MTU isn't just about making your internet work. It's about peering behind the curtain, seeing how fundamental network plumbing dictates reliability and even security. Improper MTU handling can lead to anything from sluggish downloads to completely broken VPNs, or even exploitable firewall bypasses for older systems. You now know that silent connection failures often aren't random glitches, but rather your packets slamming into an MTU wall, with the crucial feedback messages being blocked. So, MTU is the physical limit of individual packets. But if every packet is tiny, how does TCP ensure a smooth, reliable stream of data without creating too much overhead?